Welcome physiology students. This is the gas exchange and acid base workshop. Gas exchange has to do with carbon dioxide and oxygen unloading and loading into the blood. And the acid base has to do with the pH of your blood. That's handled with the amount of partial pressure of carbon dioxide in the blood. We'll be looking at this and we'll be classifying the four disorders of the acid-base pH of the blood. They will be either acidosis or alkalosis in your blood. And acidosis means your blood is slightly acidic, so anything less than 7.2. And alkalosis would be anything basic, anything greater than 7.2 or 7.24, which is normal in blood. And then in those acidosis and alkalosis disorders, we have two that are due to a metabolic reason or a respiratory reason. So metabolic acidosis has to do to a decrease in bicarbonate, which we'll talk about what that is. Respiratory acidosis is due to an increase in carbonic acid. Metabolic alkalosis and respiratory alkalosis are due to an increase in bicarbonate for metabolic alkalosis, and respiratory alkalosis is due to a decrease in carbonic acid. But first, before we get into that, we're going to watch a quick video about oxygen transport just to review how oxygen gets into the blood and how carbon dioxide gets out of the blood.
All cells need oxygen. It is the essential fuel which is necessary to enable cells to stay alive and to carry out their various activities. Bringing oxygen to the cells requires the uptake of oxygen from the air in the lungs, its transportation in the blood, and its delivery to cells all over the body. The first step is the taking up of oxygen by blood flowing through fine capillaries in the walls of the lungs' air sacs, or alveoli. The oxygen molecules change from their state as a gas freely circulating in the air, dissolving into a solution in the plasma within the capillaries of the alveoli. Once in the solution of the blood, 98% of this dissolved oxygen is taken up by passing red cells, leaving just 2% remaining in the physical solution unattached. Red cells are particularly well suited to transporting oxygen because they contain a special oxygen-binding protein known as hemoglobin. Each molecule of hemoglobin itself contains 4 molecules of heme, an iron-containing pigment, which binds oxygen loosely and reversibly. Hemoglobin that is fully saturated with oxygen is bright red and is called oxyhemoglobin. On the other hand, hemoglobin that is not saturated with oxygen is purplish blue in color and is called deoxyhemoglobin. It is heme which makes it possible for the red cells to pick up oxygen dissolved in the blood, transport it combined with hemoglobin, and release it back into the blood as oxygen in solution, ready for delivery to the various cells of the body. Hemoglobin gives up its oxygen as red cells travel through capillaries in tissues where there is a low content or partial pressure of oxygen. The partial pressure of oxygen represents the level of dissolved oxygen in plasma. As oxygen is released and again is carried in solution, the partial pressure of oxygen in the capillaries becomes greater than the partial pressure of oxygen in the surrounding tissues. This causes oxygen to move out of the capillaries into the tissues and to finally reach the cells. This graph, the oxygen dissociation curve of hemoglobin, shows why hemoglobin is particularly suited to its role in transporting oxygen. The oxygen dissociation curve demonstrates the relationship between the oxygen carried in combination with hemoglobin, the O2 saturation, and the partial pressure of oxygen in the arterial blood. The sharp upstroke and the flat plateau illustrate how oxygen is released to the tissues over a wide range of conditions. Its shape means that although the partial pressure of oxygen in the blood returning from the lungs and being pumped out by the arteries may be reduced to only 50% of the normal value, say due to lung disease or high altitude, hemoglobin will still be 85% saturated with oxygen.
All right, so let's go back to our PowerPoint. And we'll talk a little bit about this oxygen dissociation curve, what the speaker was talking about at the end of that video. The oxygen dissociation curve shows the percentage of the amount of oxygen that's bound to hemoglobin on the left side of the screen. And again, hemoglobin is the structure in red blood cells that carries oxygen. It can carry one oxygen molecule per one hemoglobin, and there's about 250 million molecules of hemoglobin per red blood cell. And then on the y-axis, you have the partial pressure of oxygen in the blood. So this is your oxygen dissociation curve with regards to the partial pressure of oxygen in the blood. And as you see here, the average pressure of oxygen of deoxygenated blood returning to the heart is about 40 millimeters of mercury, and the pressure of blood in oxygen of blood leaving the lungs is about 100. So we have about 25% of oxygen in arterial blood that's being released to tissues during rest or light exercise. And there's always this reservoir of oxygen held by hemoglobin, and it can be released to tissues with a low pressure of oxygen. So this ability of hemoglobin to bind oxygen is really important because it can release oxygen when needed. If we look at the effects of temperature and pH on this oxygen hemoglobin curve, you'll notice here that different things can affect the unloading of oxygen to the surrounding tissues. So if we just take a look at temperature, 37 degrees Celsius is normal temperature. An increase in temperature will shift the curve to the right. And all that means is an increase in temperature shifting the curve to the right means that oxygen will be more readily or more easily offloaded from hemoglobin in the body. Colder temperatures, such as the 20 degrees Celsius or 10 degrees Celsius in green and blue, shift the curve to the left. And anything that shifts this curve to the left will decrease the ability of hemoglobin to offload its oxygen. The same thing can happen for pH, and that's where we'll get into talking about the effects of pH in the blood. So 7.4 is the normal pH of the blood. If the blood gets slightly more acidic, that'll shift the curve to the right, and that'll increase oxygen unloading into the blood, into their surrounding tissues. And anything that's a more basic pH, like 7.6 in red, will shift the curve to the left and decrease unloading of oxygen into the surrounding tissues. So how this curve gets shifted will be important to the unloading of oxygen from hemoglobin into the surrounding tissues. And we will come back to this and give an example of what will happen to this curve with the effects of carbon monoxide poisoning with your last application question on your sheets. So how does pH change within the blood? Well, carbon dioxide is the main reason how your pH of your blood changes, and that's because it's transported as bicarbonate ions in the blood. So the amounts of carbon dioxide in your blood, because it's transported as a bicarbonate ion, that will affect the pH of the blood. So your body does different compensations to increase or decrease the amount of bicarbonate to change pH levels. Remember, your body tries to maintain homeostasis in all situations, so it'll do whatever it can to maintain a normal pH of 7.4 in the blood. So how is carbon dioxide transported? Carbon dioxide is also found or attached in your red blood cells, and due to carbonic anhydrase, it gets transported or changed into this bicarbonate ion and extra hydrogen ions. And that's how it gets transported in the blood, mainly as bicarbonate ions. When it gets transported, an increase or decrease amount of this bicarbonate ion will change the pH of the blood. And as we look at a couple percentages here, you can see that about 5% of all CO2 is just transported within the tissues, 20% is bound to hemoglobin itself, and 70% is actually changed into this bicarbonate ion, as you can see. So let's look at some acid-base imbalances. And as we look at this, this is a great drawing to remember what alkalosis means and what acidosis means. Alkalosis, remember, is anything more basic, so anything greater than 7.4, which is normal blood pH. So we say alkalosis is kicking up the pH to help you remember, and acidosis slipping down the pH scale, because anything less than 7.4 will be considered an acidosis, pH imbalance in the body. And as we look at these different disorders, I'm going to draw your attention to this equation. So this equation shows that picture of what happens to carbon dioxide when it gets transported in red blood cells. So when we add water, a hydrolysis reaction, we add water using the enzyme carbonic anhydrase. Again, about 70 carbon dioxide gets transformed to carbonic acid, and carbonic acid breaks into bicarbonate ion and hydrogen ions. And again, about 70% of carbon dioxide gets transported in the blood as this bicarbonate ion. This hydrogen ion, depending on the relative amounts of hydrogen ions, that'll increase or decrease the blood pH. Due to Le Chatelier's principle, and I'm a chemistry nerd because that was my major in college, this equation always needs to be balanced. So if we have more carbon dioxide in the blood, we'll have more hydrogen ions in the blood. And the amount of hydrogen ions is what will determine the pH. If we have a lot of hydrogen ions, that means your blood will be more acidic. And if we have less hydrogen ions, that amount will be more basic. And the same thing goes for the bicarbonate ion. We need to keep these equations balanced, and that will, the body will do that in order to compensate for any change in pH. So if we look at the first imbalance, we have respiratory acidosis. A key feature of respiratory acidosis, it can be diagnosed if a patient is breathing shallowly, maybe they have pneumonia or emphysema, so they're not getting enough carbon dioxide out into the blood. So carbon dioxide, because they're not able to breathe very well due to pneumonia, emphysema, something else, carbon dioxide will actually accumulate in the bloodstream because they're not able to breathe it out. And we need to get rid of carbon dioxide because it's a waste product of our cells. So respiratory acidosis will be characterized by falling blood pH and rising pressure of CO2 in the blood. And that's because respiratory acidosis, if we have an increase on this side of the equation of carbon dioxide, an increase on this side of the equation, remember balanced equations from chemistry, we're going to have an increase in these hydrogen ions on the other side of the equation, because that's how carbon dioxide is transported in the blood. So falling blood pH means our blood pH is becoming very acidic. So how does the body compensate for this and try to correct itself even before any medical professionals get involved? Well, the kidneys, we usually call this renal compensation when the kidneys are involved. Since our HCO3 bicarbonate ion levels are above normal, your kidneys will actually try to retain excess bicarbonate ion. And by retaining excess bicarbonate ion, they're trying to increase your blood pH because it's so acidic at this point. So that's respiratory acidosis. We have an accumulation of CO2 in the blood characterized by falling blood pH and rising pressure of CO2. And again, this is just a reminder to show how CO2 gets carried within red blood cells. Again, most of it's carried as this bicarbonate ion, about 70% of it. But we want to breathe it out. So if anyone has too much CO2, they'll have a falling blood pH because they'll have too many of these hydrogen ions, which will lower their pH. The next acid-base imbalance is respiratory alkalosis. So again, alkalosis, we're dealing with a greater pH than 7.4. And this is characterized by CO2 actually leaving the body faster than it's being produced. So how is someone getting rid of CO2 faster? Well, they're probably hyperventilating. They're breathing out due to stress, some sort of other reason. Their body is hyperventilating. When they get rid of too much CO2, that is a bad thing because that will increase their blood pH, making it more alkaline or basic. So this is a respiratory alkalosis. So this is characterized by an increased blood pH and a decreased pressure of CO2 relative amount in the blood. So if we have too much carbon dioxide leaving the body, that is also a bad thing because then we'll get a more alkaline or basic pH to our blood. For respiratory alkalosis, your kidneys also kick into gear. So the compensation is also renal because your bicarbonate levels are below normal because we have less CO2 in the body. And remember, CO2 is mostly transported or it's transmitted in the blood as bicarbonate ion. Your kidneys secrete or do not absorb any CO3 to try to increase the amount of CO2 in the blood as possible because we have too much leaving. Then we get to metabolic acidosis. So an acidosis, again, is a decrease in blood pH. So this will be characterized by falling blood pH levels and HCO3 levels. So we have an increase in acetic acid, which could be due to a variety of things, and a loss of HCO3. Lactic acid usually will accumulate in this metabolic acid, and lactic acid can accumulate due to an increase in exercise. An increase in acetic acid can also accumulate due to a variety of reasons as well. The compensation for this is respiratory, where your respiratory rate and depth will elevate due to decreasing PCO2 levels and increase pH levels. So metabolic acidosis, again, is characterized usually if you're ingesting something that's more acidic or you're losing HCO3 because you have less CO2 in the blood, or lactic acid is accumulating due to exercise. So we have an acidosis imbalance. Again, falling blood pH because we have less CO2 in the body leads to less hydrogen ions. And your respiratory rate will also change this. So you'll try to hyperventilate to decrease the amounts of CO2 in the body and increase the pH levels. And then the last, metabolic alkalosis, can sometimes be due to the intake of excess base due to antacids. So again, alkalosis is a pH above 7.4. Vomiting, so losing any sort of liquid can also lead to an alkalosis, vomiting, diarrhea, and this will lead to rising blood pH and HCO3 levels. So your HCO3, your bicarbonate levels are increasing, and your pH is greater than 7.4 because we're dealing with another basic imbalance. The compensation is also respiratory. You'll get more slow, shallow breathing to increase the amounts of carbon dioxide in the blood. So you want to retain more carbon dioxide in the blood to try to decrease pH levels. So at this point, I'm going to let you guys pause the video and complete your application questions, and then we'll go through the application questions together. So your first application question has to do with determining what the patient has and what she should be diagnosed with. And if he has a pH of 7.28, we know we're dealing with an acidosis patient, and low pH and CO3 levels points to this condition of metabolic acidosis. And metabolic acidosis, some causes to this acid-base disturbance could be high alcohol consumption, persistent diarrhea, renal disease, or starvation. And number two, and again, feel free to pause the video at any time if you're working through this, has to do with carbon monoxide. And it says, knowing that carbon monoxide has a much higher affinity for hemoglobin than oxygen, explain how carbon monoxide affects oxygen delivery to tissues. And this is really important, especially living here when many people have gas furnaces. I would encourage you guys all to get a carbon monoxide detector in your homes near your gas furnace. But carbon monoxide poisoning is very dangerous because carbon monoxide will decrease the total oxygen carrying capacity of blood by occupying those hemoglobin oxygen sites itself. The affinity between hemoglobin and carbon monoxide is approximately 230 times stronger than the affinity between hemoglobin and oxygen. So carbon monoxide will actually bind to hemoglobin in preference to oxygen. Hemoglobin binds oxygen avidly, making it difficult for oxygen release to the tissues. So because carbon monoxide is filling up those oxygen sites on hemoglobin, hemoglobin actually kind of holds on to oxygen even tighter because it realizes something isn't right. So it doesn't even release the oxygen that it does have with it. It's asking for what effect would carbon monoxide have on the oxygen dissociation curve. And remember that any effect where the hemoglobin holds on to oxygen tighter always shifts the curve to the left. So it will shift the oxygen dissociation curve to the left because hemoglobin is becoming not more saturated with oxygen, but it's holding on to it tighter, so it's not going to release it as quickly as it normally would. The binding of carbon monoxide at one of these sites increases oxygen affinity in the remaining 3 sites. So that just means that it won't release it as much. What treatment would be given to someone who has carbon monoxide poisoning? Administering 100% O2 right away is important. Putting them in a chamber with hyperbaric oxygen is also a treatment used to try to get oxygen into their body as quickly as possible. And the last part, there should be a crossword that you guys can do on your own that goes with this workshop. And for your activity for this workshop, you'll do kind of a house clinic duty of role-playing patients and doctors. And that'll also help you kind of review those acid-base imbalances. Thanks for listening, guys.